Hello! We stated Myerson's lemma last time, which tells us that we can get a DSIC payment rule as long as we have a monotone allocation rule. This is the simple rule that the more you bid, the more you get. Also, this payment rule is unique if we assume that bidding 0 means paying 0. We will now prove parts of the result. We begin with this lemma. If an allocation rule X is implementable, then it is monotone. This means that if we ever hope to get a DSIC payment rule, this allocation rule must be a monotone one. We start by supposing that X is implementable. This means that there exists a payment rule P such that XP is DSIC. And we need to prove that X must be monotone. We start by fixing a player I and the bids B minus I for the other players. For simplicity of notation, we will use x of y and p of y to represent xi of y b minus I and pi of y b minus I. These are the allocations and the payments for player I if they bid y. So we want to prove that if y is at least z, then x of y is at least x of z. If you bid more, the allocation is higher. So we will assume that y is at least z. And here is the key observation that we need in this proof. And that is, the rules x and p are defined independent of the player's valuations. So it doesn't matter what the player's valuations are, xp is going to be DSIC. In particular, xp is DSIC if player i's valuation is y. This means that bidding truthfully should give you the highest utility. So the utility of bidding y is at least the utility of bidding z. Remember that the utility of a player is their valuation times what they get minus their payment. So the utility of bidding y is y times x of y minus p of y. And this is at least y times x of z minus p of z, the utility of bidding z. Remember that y here is the valuation of player I. Also, xp is DSIC if player i's valuation is z. We can use the same argument to get z times x of z minus p of z is at least z times x of y minus p of y. The utility of bidding z is at least the utility of bidding y. We can now rearrange these two inequalities to get the following. Z times x of y minus x of z is at most p of y minus p of z, which is at most y times x of y minus x of z. This is called the payment sandwich, which holds for DSIC rules. We will use this again very soon. Now, if we look at the two ends of the sandwich, we have z times something is at most y times the same thing. But since y is at least z, which is at least 0, we get that this something, x of y minus x of z, must be at least 0. So, x of y is at least x of z, and that completes our proof that x is monotone. Now the converse is, if x is monotone, then x is implementable, meaning you can find a payment rule such that it is DSIC. We will only prove the case where x is piecewise constant. Here is our approach to this proof. We will assume x is monotone and also xp is DSIC. We will then derive a formula for p, and p is unique, assuming that the payment is 0 whenever the bid is 0. This formula is then the only candidate payment rule that could work under DSIC. We then have to prove that using this particular payment rule, xp is indeed DSIC. Since we will be proving this for the case where x is piecewise constant, we will now describe a generic x that is both monotone and piecewise constant. The graph will look something like this. We see that there are some jump points along the way. Z1 bar, Z2 bar, all the way up to ZQ bar in this order, such that x is constant in the intervals between the z's, from 0 to Z1 bar, Z1 to Z2 bar, etc. We now define hj to be the height of the jump at zj bar. More precisely, hj is the limit when w is approaching zj bar from the right, x of w minus x of zj bar. And we can write all the monotone piecewise constant function in this way, assuming that it starts at 0. And here is the first of the two parts of the converse that we will be proving. If x is monotone and piecewise constant, and xp is DSIC with pi of b is 0 whenever bi is 0, then p is unique. For our proof, we will derive the formula for p one piece at a time. We first show that p is also piecewise constant. This means that if z is inside an interval, the derivative p prime of z is 0. Have I mentioned that there might be some calculus in this lecture? We now assume that y is strictly greater than z. We suppose that z is in some interval, from zj bar to zj plus 1 bar for some j. We assume DSIC, so the payment sandwich applies. We take the payment sandwich and divide each term by the positive number y minus z. This will give us this series of inequalities. You might notice something familiar with this. We are going to take the limit as y approaches z from the right. Taking this limit for x of y minus x of z over y minus z gives us x prime of z. And this is just 0, because x is constant at z. So both ends of the inequalities approach 0. If you remember from calculus, we can use the squeeze theorem to say that the limit of the middle term is also 0. But this limit is just p prime of z. So this tells us that whenever z is within an interval defined by x, the payment rule is flat. So p is also piecewise constant with jumps at the same places, z1 bar to zq bar. Now that we know what p looks like within the intervals, we need to figure out what are the jumps for p. We let z be zj bar for some j. Once again, we will look at the payment sandwich. We will take the limit of each term as y goes to z from the right. So this limit for y times x of y minus x of z is z times h of j, the jump of x at zj bar. The limit for z times x of y minus x of z is also z times hj. Using the squeeze theorem again, the limit of p of y minus p of z is also z times hj, which is equal to zj bar times hj. So the payment jump at zj bar is zj bar times hj. So we know that p is a piecewise constant function where, at each of these jump points, it will jump up by this much. But this does not uniquely define p, and that is why we need the assumption that p of 0 is 0. That will give us the starting point that we need, so this uniquely defines the function p. We now put it into one formula. Suppose we have an arbitrary z. If j is the largest index where z is at least zj bar, then the payment at z, which is p of z, is equal to the sum of k from 1 to j, zk bar times hk. This means that starting at 0, we will go through all the jumps required to get to z and sum them together. And we have derived a unique formula for p, and that completes our proof of the lemma. Now let's try to visualize what the payment rule means on the graph for the allocation rule x. Suppose our x has these two jumps, and z comes after the second jump. The payment rule is z1 bar h1 plus z2 bar h2. Can you see what this means on the diagram? Z1 bar h1 represents the area of this rectangle here, and Z2 bar h2 is the area of another rectangle. So this means that the payment is essentially the area to the left of the graph of x. Now we have only shown that being DSIC implies that P is this formula. We still need to show that P is indeed DSIC. So the lemma is, the payment rule P from our previous lemma is DSIC. And we will prove this by picture. We will compare the utility of bidding a player's valuation versus bidding lower and bidding higher. Take a look at this graph for our piecewise constant allocation x. Can you find the area that represents the value that is received by the player, the payment, and the utility? The value received is the valuation times the allocation, so it is this rectangle here. The payment is to the left of the graph, so it is this green area here. So the utility is the difference between the two, which is this pink area here. So this is the utility we get if we bid our valuation. Now let's take a look at what happens if we underbid. Suppose our new bid is here. Can you find the areas that represent value received, the payment, and the utility? We have a smaller allocation this time, but our utility is still the same. So the value received is this smaller rectangle. At the same time, the payment is also smaller, which is in this area. And the difference is the utility. Notice that this utility is smaller than the one we had from before. Now let's do the same exercise in a case where we overbid. Can you find the three relevant areas here? This time, we have a higher allocation, so our value received is also higher. But our payment is also larger than before. If you look at the utility, it is actually this first area minus the second area. We have paid a little bit too much. So this utility is also smaller than the original utility. So the utilities for 2 and 3 are at most the utility of 1. And the utility of 1 is non-negative. Therefore, our payment rule is DSIC, and that completes our sketch proof. So that completes our proof of Myerson's lemma for piecewise constant allocation rules. We will apply this result to the two auctions we have seen so far in the next lecture.